April 6th, 2026 started as a completely ordinary day for the team monitoring a ring-shaped radio telescope in the Russian Caucasus mountains. Routine scans, routine data, the same quiet hum of the universe going about its business. And then, in the middle of that ordinary morning, something came through from 29,000 light-years away. A giant radio burst, so powerful it briefly made one single object the brightest radio source in the entire Milky Way galaxy. The object is called Cygnus X-3. Scientists have been studying it for nearly 60 years, and they still cannot fully agree on what it is. Tonight we figure it out together. If you're new here, subscribe and get comfortable. Because what this object actually is, and why it just did this twice in 80 days, is the strangest story in modern astronomy, and we're just getting started. Part 1. The Arrival. Something arrived on April 6th, 2026, and nobody was ready for it. Not because it was unexpected in the way a crisis is unexpected. The telescope had been watching, the astronomers had been monitoring, the data had been flowing. But there is a difference between watching a quiet ocean and watching a quiet ocean that suddenly produces a wave the size of a skyscraper. And on that morning, the ocean produced a wave. The instrument that caught it is called Russian 600, and it sits in the Caucasus Mountains of southern Russia. And it is not a dish the way most people imagine a radio telescope. It is a ring. A full circle of metal panels, 576 meters in diameter, roughly the circumference of 6 city blocks arranged in a loop, and it sweeps the sky continuously, day after day, frequency after frequency, and most of what it hears is the ordinary background hum of the universe going about its business. Faint sources, stable sources, objects that behave themselves. Cygnus X-3 had not been behaving itself. At the moment of detection, the signal arrived across a spread of frequencies from 4.7 GHz all the way up to 30 GHz, and the brightness of it, what astronomers call the flux density, peaked at 6.6 Jansky at 11.2 GHz. Those numbers probably mean nothing to you yet, so let me put them in context. The typical radio brightness of Cygnus X-3, when it is sitting quietly between episodes, runs somewhere between 3 and 30 millijansky. 1 millijansky is 1,000th of a Jansky. So in the span of a detection event, this object went from something like 10 millijansky to 6.6 Jansky. That is not a small fluctuation. That is an amplification of brightness by a factor of several hundred, and it happened fast enough that the telescope caught it mid-rise. For a window of hours, Cygnus X-3 became the brightest radio source in the entire Milky Way galaxy. Not the brightest in that patch of sky, the brightest in the galaxy, the entire galaxy. An object 29,000 light-years away, completely invisible to the naked eye, buried behind layers of interstellar dust so thick that not a single optical photon gets through, briefly outshone everything else our galaxy produces in radio light. And here is the detail that should stop you cold. This was not the first time it had done this recently. Roughly 80 days earlier, in January of 2026, Cygnus X-3 produced another giant radio flare. A precursor event, in the language of the astronomers who published the alert through the astronomers' telegram system, which is essentially an emergency broadcast network for the global astrophysics community. 2 giant flares in 80 days from a system that had previously separated similar events by months or years. Something in that system has changed, and we do not yet know what. The signal that arrived on April 6th had been travelling for 29,000 years. It left its source when the human beings alive on this planet were not farming, not building cities, not writing, not doing anything we would recognise as civilization. It crossed the galactic plane, threading through clouds of gas and magnetic fields and the debris of ancient stellar explosions, and it arrived at a ring of metal panels in the Russian mountains and was recorded, classified and broadcast to the global astronomy community within hours. We have been watching Cygnus X-3 since the 1960s, over half a century of observation, thousands of papers, multiple space telescopes, ground-based arrays, gamma-ray detectors, and the honest summary of where the science stands is this: we still do not fully know what we are looking at. We do not know what the compact object at its centre is. We do not know why it flares when it does. We do not know why the flares are coming faster now. Whatever is happening 29,000 light-years away in the direction of the constellation Cygnus, it is happening more urgently than before, and the signal is arriving louder, and the universe is, in its patient and indifferent way, asking whether we are paying attention. We are. But we are also still confused, and that confusion is, in its own strange way, the most interesting part of the story. Part 2. The Time Paradox. Before we go any further into what Cygnus X-3 actually is and what it is doing, I want you to sit with something for a moment, because it does not get easier the more you think about it. The radio photons that arrived at Russian 600 on April 6, 2026, left their source approximately 29,000 years ago. Not metaphorically, not as a rough approximation. The speed of light is a hard limit, and at that speed, crossing 29,000 light-years takes 29,000 years, and there is no workaround, no shortcut, no rounding down. 29,000 years. 29,000 years ago, the most sophisticated human technology on Earth was a sharpened stone. The caves at Chauvet, in what is now southern France, were being decorated with paintings of lions and rhinoceroses and horses, hands pressed flat against rock and outlined in ochre and charcoal. The artists who made those paintings were anatomically identical to you. Same brain size, same cognitive architecture, same capacity for abstract thought. But there was no agriculture anywhere on Earth, no domesticated animals, no written language, no city, no road, no wheel. The human population of the entire planet was probably somewhere between 1 and 2 million people, scattered in small groups across a world that had no name for itself. And at that exact moment, 29,000 years ago, something happened in a binary star system in the direction of what those humans would one day name the constellation Cygnus, and the light from that event began its journey toward us, and it arrived while a radio telescope in the Caucasus Mountains was pointed at the right patch of sky. This is what astronomers mean when they talk about observation as a form of time travel. There is no such thing as looking at a distant object in real time. When you look at the moon, you are seeing it as it was 1.3 seconds ago. When you look at the sun, you are seeing it as it was 8 minutes ago. When you look at the nearest star beyond our solar system, you're seeing it as it was 4 years ago. And when you detect a radio flare from Cygnus X-3, you're observing a physical event that occurred before the last ice age reached its maximum extent on this planet. This creates a genuinely strange epistemic situation for the scientists studying it. The flare they recorded in April of 2026 is not what Cygnus X-3 is doing now. It is what Cygnus X-3 was doing 29,000 years ago. Whatever that system is doing in what we would call the present, that information will not reach us for another 29,000 years. The object we're studying in such urgent detail does not exist for us in any contemporaneous sense. We're doing cosmic archaeology, sifting through ancient light, and the puzzle we are trying to solve is whether the behavior encoded in that ancient light tells us something meaningful about a system that, in real astronomical terms, may have already changed beyond recognition. And yet the urgency is real, because the pattern in that ancient light is itself changing. The gap between major flares is shrinking. The behavior is accelerating. Whatever happened 29,000 years ago to produce the January flare, and then whatever happened 29,000 years ago to produce the April flare 80 days later, those two events are separated in real time by 80 days, even if we received them with a 29,000-year built-in delay. The acceleration is encoded in the ancient signal. The mystery is real, and it is deepening. The signal also had to survive the journey. It did not travel through empty space. The galactic plane, that dense band of gas and dust and magnetic fields that you can see as the Milky Way on a dark night, is a maze of obscuring material. Visible light from Cygnus X-3 never makes it through. The dust extinction is total, but radio waves are long enough to slip between the dust grains, to propagate through the interstellar medium like sound through a wall that would stop a bullet, and so the signal arrives at our detectors carrying information that no other wavelength could have delivered intact. We are hearing an ancient event through the one channel the galaxy left open for us. And what we are hearing is something getting louder. Part 3. The telescope that heard it. The reason we caught this at all comes down to the particular character of Russian 600, and it is worth spending a moment here because the instrument shapes the science in ways that are easy to underestimate. Most radio telescopes are dishes, single parabolic surfaces that focus incoming radio waves to a central receiver, pointed at one spot in the sky at a time. They are extraordinarily sensitive, but they are also inherently narrow in their field of view. Russian 600 is different. Its ring geometry means that as the Earth rotates, the telescope sweeps a strip of sky, covering a wide range of objects in a single daily pass. It also operates simultaneously across a broad range of frequencies, which is exactly why the April 6th detection was so richly characterized immediately. The multi-frequency profile of the flare, from 4.7 to 30 GHz, was captured in a single sweep, not assembled from multiple pointed observations over hours or days. This matters for catching transient events, objects and phenomena that change quickly. A giant radio flare from a microquasar can rise and fall in hours. If you're not pointed at it at the right moment, you miss the peak. Russian 600 scanning architecture means that Cygnus X-3 gets observed every single day at multiple frequencies, regardless of whether anyone has specifically scheduled it as a target. It is a permanent fixture in the daily monitoring log. The result is that when something unusual happens, the detection is not lucky. It is structural. The system is designed to catch this kind of event, and crucially, when the alert goes out through the astronomer's telegram network, other telescopes around the world and in orbit can be rapidly redirected to follow up. The telegram system is how the global astronomy community coordinates rapid response to transient events, and within days of the April 6th detection, follow-up observations were being planned across multiple wavelength regimes. But here is what should stay with you as we go forward. Even with this level of monitoring, even with daily observations across multiple frequencies for decades, Cygnus X-3 still managed to surprise the people watching it. The flare arrived. It was enormous, and nobody had predicted it. Whatever is driving the changing behavior of this system is not something the current models anticipated, and that is precisely what makes the story worth telling. Part 4. The frequency coincidence. There is something about this detection that caught the attention of people far outside the astronomy community, and it has to do with the frequency range of the signal. 4.7 to 30 GHz. If you have a smartphone, your Wi-Fi and cellular connections operate in the 2.4, 5 and 6 GHz bands. Your microwave oven operates at 2.45 GHz. Satellite communication systems operate across much of the same range. So when the headline says a cosmic signal arrived at the same frequency as your phone, that is technically accurate, and it sounds alarming in a way that deserves to be dismantled carefully. The reason these frequencies overlap is not mysterious. It is atmospheric. The Earth's atmosphere is largely transparent to radio waves in this frequency range, meaning they pass through without being absorbed. This is why both cosmic radio sources and human communication engineers favour these frequencies, but for completely independent reasons. We built our technology around the window the atmosphere provides. The universe does not know or care about our window. Cygnus X-3 emits radio waves at these frequencies because of the physics of relativistic plasma and magnetic fields, not because of any alignment with human infrastructure. The signal also carries no structure, no encoding, no information in any communicative sense. It is the broadband radio emission of charged particles spiraling around magnetic field lines at speeds approaching the speed of light. It is beautiful physics. It is not a message. The intensity of the signal at Earth, after travelling 29,000 light-years, is so vanishingly small that no instrument you own would register it as anything other than noise below the noise floor. The 6.6 Jansky brightness is an astronomical measurement, calibrated for instruments designed to detect the faintest possible signals. Your phone would not notice it. The real anomaly here is not the frequency, it is the behaviour, and that is where the story actually lives. Part 5. The real anomaly. Let me pull back from the detection itself and show you what the detection means in context, because the context is where the real alarm lives. Cygnus X-3 has been producing giant radio flares since astronomers first noticed it was capable of doing so. The history of these events is documented but irregular. In 2011, a giant flare was observed. In the period between 2016 and 2017, multiple flare events were recorded, separated by roughly 200 days. These were already considered unusual because of their intensity, because of the way they briefly repositioned Cygnus X-3 at the top of the Milky Way's radio brightness rankings. But the cadence, the rhythm of the events, was slow enough to fit within a framework of irregular but roughly understood accretion physics. Then January 2026, a giant flare. Significant enough to trigger alerts, significant enough to prompt multi-wavelength follow-up campaigns across the global telescope network. And then, before those campaigns had fully concluded, before the interpretations of the January event had been finalized, before the papers were written, 80 days later, April 6th, another giant flare. Not a minor event. Not a repeat at reduced intensity. Another full-scale giant flare, peaking again at values that made Cygnus X-3 the brightest radio source in the galaxy. There was also a smaller event in February 2026 between the two giants, a mini-flare in the language of the observers who logged it. Possibly a sign of instability in the accretion disk, possibly a failed jet launch that released some of the stored energy before the full ejection event in April. The system was not quiet between the January and April flares, it was restless. The compression of the timeline is what matters here. 200 days between events in 2016 and 2017, 80 days between events in 2026 with a smaller event in between. If this is a trend, if the cycle is genuinely shortening, it implies that something in the engine of Cygnus X-3 is operating differently than it did a decade ago. The mass transfer rate from the companion star may have increased. The accretion disk may be cycling through its instability modes faster. The magnetic geometry that governs jet launching may have shifted into a new configuration. No consensus exists yet among the researchers who study this system. The models that exist for microquasar flare behavior were built on the slower historical cadence, and the 2026 data does not fit comfortably inside any of them. What the scientists do agree on is that something has changed, that the system is behaving in a way it has not behaved before in the observational record, and that the implications of that change are still being worked out. Something in that system has shifted. We can see the effects. We cannot yet explain the cause. And that is exactly the kind of problem that keeps astrophysicists awake at night, because a system you cannot explain is a system that can still surprise you. And Cygnus X-3, as you're about to find out, has been surprising people since the 1960s. Part 6. What is Cygnus X-3? The name tells you something about the history of how it was found. Cygnus refers to the constellation, that cross-shaped pattern of stars in the northern summer sky that ancient astronomers imagined as a swan in flight. The X means X-ray, and the 3 means it was the third brightest X-ray source detected in the direction of Cygnus when early X-ray surveys began cataloguing the sky in the 1960s. Those early surveys were done with instruments carried on sounding rockets, and later early X-ray satellites, because Earth's atmosphere blocks X-rays completely. To see X-ray sources, You have to get above the atmosphere, and in the early space age that was a new and expensive capability. What the X-ray surveys found was a source of powerful variable X-ray emission, bright, flickering, changing on timescales of hours and days. That variability immediately suggested a compact object, because only things with very small physical dimensions can change their brightness on short timescales. A large, diffuse object cannot brighten and dim in hours, because light takes hours to cross it, and you cannot have a coordinated brightness change faster than light travel time across the emitting region. Something small was responsible, and something small producing that much energy in X-rays meant something gravitationally extreme. What we know now is that Cygnus X-3 is a binary system. Two objects, locked in mutual gravitational orbit, separated by only a few solar radii, completing one full orbit every 4.8 hours. To put that in perspective, Mercury, the innermost planet in our solar system, takes 88 days to orbit the Sun. The Moon takes 27 days to orbit Earth. The entire Cygnus X-3 system completes its orbit in under 5 hours. That is not just fast. That is a system in which the two objects are practically on top of each other, gravitationally speaking, circling at distances comparable to the size of a single star. One of those objects is a Wolf-Rayet star, an extremely massive evolved star in the final stages of its life, burning hot and fierce and shedding its outer layers at a ferocious rate through a dense, fast stellar wind. We will spend more time on this star shortly, because it is central to everything that makes Cygnus X-3 what it is. The other object is compact, small, extraordinarily dense. It is either a black hole or a neutron star, and after 60 years of observation, we genuinely do not know which. It sits inside the envelope of the Wolf-Rayet stellar wind, accreting matter, generating X-rays, and periodically launching jets of relativistic plasma perpendicular to its accretion disk. Those jets are what we detect as radio emission. Those jets are what produce the April 6th flare. And those jets are, in a very real sense, the most powerful continuous energy output in the Milky Way per unit of compactness. Everything in this system is running at extremes. The orbital period is extreme. The mass loss from the companion star is extreme. The jet power is extreme. The multi-wavelength emission is extreme. And the behaviour in 2026, with giant flares arriving faster than they ever have in the observational record, is extreme in a new and still unexplained way. This is not a system that has one remarkable property. It is a system that seems to be remarkable in every direction you look, and that accumulation of extremes is exactly why 60 years of study has not produced a settled understanding of what, at its core, it actually is. Part 7. The Impossible Classification. Here is something that should tell you a great deal about where astrophysics stands with Cygnus X-3. It has been assigned, in peer-reviewed literature, to at least 4 distinct and partially contradictory categories of astrophysical object, and the scientists responsible for each classification are not wrong. It is a microquasar. That classification goes back decades and describes the relativistic jet behaviour, the accretion disk physics, and the radio emission morphology that mirrors, at stellar mass scales, the behaviour of quasars, which are supermassive black holes accreting matter at the centres of distant galaxies. A microquasar is essentially a quasar running on a compact object, with a mass measured in solar masses rather than billions of solar masses, and Cygnus X-3 fits that description well. It is also a gamma-ray emitter. The Fermi Space Telescope and the Italian Agile satellite both detected gamma-ray emission from Cygnus X-3 that is orbitally modulated, meaning it rises and falls in sync with the 4.8-hour orbital period of the binary system. This confirms the gamma-ray emission originates within the system itself, not from some background source, and it puts Cygnus X-3 in a relatively small category of high-mass X-ray binaries that produce gamma rays. In 2024, analysis of data from the Imaging X-ray Polarimetry Explorer, IXPE, showed that Cygnus X-3 shares key properties with a class of objects called ultraluminous X-ray sources, or ULXs. These are objects in other galaxies that appear impossibly bright in X-rays, so bright that they seem to violate the physical limit on how much radiation a given mass can emit. The IXPE findings suggested the extreme apparent brightness in both Cygnus X-3 and distant ULXS results from a funnel-shaped geometry in the accretion disk that collimates the emission and directs it toward observers, creating the impression of greater luminosity than actually exists. This reframed Cygnus X-3 as a local, nearby laboratory for understanding objects that, in other galaxies, we can only see as unresolved points of light. And then in 2025, the LHAASO Observatory in China, a massive array of particle detectors spread across a high-altitude plateau in Sichuan province, confirmed that Cygnus X-3 is a pevatron, a source of particles accelerated to energies measured in peta-electron volts, energies so extreme that they had previously been associated only with supernova remnants, the most violent stellar explosions in the galaxy, and with the enormous jets of active galactic nuclei. Finding those energies in a stellar mass binary system meant the jets of Cygnus X-3 are doing something to particles that we did not fully expect them to be capable of doing. Microquasar, gamma-ray binary, ULX analog, pevatron. Each label is real. Each label implies a different dominant physical regime, and none of them, individually or in combination, produces a unified model that explains all the observations simultaneously. The system is not behaving as any single category predicts, and the 2026 flare acceleration is happening in a system that was already resisting categorization. Whatever is driving the faster flare cadence is occurring inside an object we cannot yet fully describe. That is not a comfortable place to be doing science, but it is an honest place. Part 8. The hidden object. The most fundamental question about Cygnus X-3 is also the one that remains completely unresolved. What is the compact object at its centre? This sounds like a question that should have an answer by now. 60 years of observations, dozens of dedicated studies, multiple space telescopes operating across every accessible wavelength from radio to gamma rays. And yet the question of whether the central engine of Cygnus X-3 is a black hole or a neutron star has no settled answer, and the reasons for that ambiguity are themselves instructive about how difficult this system is to study. The most direct way to determine what a compact object is involves measuring its mass. A neutron star has a maximum mass of roughly 2 to 3 times the mass of the Sun before its own gravity overcomes the neutron pressure supporting it, and it collapses into a black hole. So a compact object measured at, say, 5 solar masses would almost certainly be a black hole. The problem with Cygnus X-3 is that measuring the mass of the compact object requires knowing the orbital dynamics of the system precisely, which requires optical or infrared spectroscopy of the companion star, which requires seeing the companion star, which is impossible because the system is buried so completely behind interstellar dust that no optical photon gets through. The dust extinction towards Cygnus X-3 is severe enough to dim optical light by a factor of roughly 10 trillion. Not 10 times dimmer, not 1,000 times dimmer, 10 trillion times dimmer. The companion star, which is itself an extraordinarily luminous object, is completely invisible in optical wavelengths from Earth. Infrared observations can penetrate some of the dust, but the interpretation of those observations is complicated by the dense stellar wind surrounding the system, which distorts the spectral signatures used to infer masses and orbital velocities. The result is that current estimates for the mass of the compact object span a range from roughly 2 solar masses to 14 solar masses. That range straddles the neutron star to black hole boundary entirely. A 2 solar mass compact object might still be a neutron star. A 14 solar mass object would certainly be a black hole. The actual answer lives somewhere in that range, and we cannot yet narrow it down further. The inclination angle of the system, meaning how tilted the orbital plane is relative to our line of sight, also affects every calculation, and that angle is itself uncertain. A system viewed nearly edge-on produces different observed signatures than the same system viewed at a moderate angle, and the geometric uncertainty compounds the mass uncertainty in ways that have prevented a clean resolution. What this means for the story we're telling is significant. The engine driving the 2026 flare acceleration is hidden from us in a fundamental sense. We are watching the exhaust of an engine we cannot see, inferring the engine's behaviour from what the exhaust tells us, and we cannot even agree on what kind of engine it is. The effects are visible and dramatic. The cause is obscured behind stellar wind and interstellar dust and 60 years of unresolved debate. And in that gap between observation and understanding, the flares keep arriving. Part 9. The Wolf-Rayet star. The compact object does not exist in isolation. It lives inside the stellar wind of one of the most extreme types of star in the galaxy, and that star is fundamental to everything happening in 2026. Wolf-Rayet stars are what happens when a star born with a mass somewhere above 25 to 30 times the mass of the Sun burns through its nuclear fuel so fast and runs so hot that it cannot hold on to its outer layers. The radiation pressure from within literally drives the surface material away in a continuous, powerful wind. The result is a star that has shed its hydrogen envelope entirely and is now exposing its hot inner core directly to space, blazing at surface temperatures of 50,000 to 100,000 Kelvin, compared to the Sun's 5,800 Kelvin, and losing mass at a rate that would drain the entire Sun in roughly 1 million years. For Cygnus X-3, this means the compact object at the system's centre orbits inside a thick cocoon of this wind material, constantly bathed in matter flowing outward from the Wolf-Rayet companion. Some of that wind falls inward, captured by the gravity of the compact object, and joins the accretion disk that powers the X-ray emission and the jets. The density of the wind environment is part of what makes the radio flares so bright when they occur, because the relativistic plasma ejected in the jets slams into this dense medium and produces the synchrotron shock emission that we detect. The Wolf-Rayet star is also temporary in the cosmological sense. It is burning fast and shedding mass fast and approaching the end of its nuclear fuel supply on a timescale of tens of thousands to hundreds of thousands of years. At some point it will undergo core collapse and explode as a supernova, or collapse directly into a compact remnant. The system will be transformed. But in the shorter term, the critical question is whether the mass loss rate from this star is changing on observable timescales, because if the wind feeding the compact object has recently intensified, that could explain why the accretion disk is cycling faster and the flares are arriving more frequently. The star may be entering a more aggressive mass loss phase in the lead up to its eventual explosion, and we may be watching the compact object respond in real time to a changing food supply. That possibility that the 2026 flare acceleration reflects the Wolf-Rayet star's own evolution connects the recent detections to a stellar death process playing out over geological timescales. The flares are not just astrophysical curiosities. They may be reading the death clock of a star. Part 10. A system smaller than the Sun. Let me give you a scale comparison that I find genuinely difficult to hold in my mind, even after thinking about it many times. The entire Cygnus X-3 binary system, both objects and the orbital path between them, fits within a volume comparable to the size of the Sun. The orbital separation between the compact object and the Wolf-Rayet star is only a few solar radii. The Sun has a radius of roughly 696,000 kilometers. The two objects in Cygnus X-3 are separated by something like 2 to 4 times that distance. If you place the Sun at the center of the Cygnus X-3 orbit, both objects would be within the Sun's outer envelope. This compactness is not incidental. It is the source of everything extreme about the system. The gravitational interaction between two objects is inversely proportional to the square of the distance between them, which means that halving the distance quadruples the gravitational force. The tight orbital geometry of Cygnus X-3 means that gravitational effects that would be modest at larger separations are amplified enormously here. The tidal forces on the Wolf-Rayet star from the compact object, the rate at which wind material is funneled toward the accretion disk, the efficiency with which orbital energy drives accretion processes, all of these are enhanced by the proximity. The 4.8-hour orbital period is a direct consequence of this compactness. Orbital period is determined by the separation and the total mass of the system, and at these separations the orbital velocity must be extraordinary to maintain the orbit. The two objects are racing around each other at speeds of hundreds of kilometers per second. The accretion disk, the jets, the wind interaction zones, all of these physical processes are occurring in an environment where the gravitational and kinetic energies involved are extreme by any astrophysical measure. When the flare recurrence accelerated from 200 days to 80 days between 2017 and 2026, that acceleration may partly reflect how sensitively such a compact system responds to even small changes in the mass transfer rate or disk conditions. There is very little damping in a system this tightly coupled. Changes propagate quickly, instabilities grow fast, and the fact that two giant flares arrived within 80 days of each other may be telling us that the system's feedback cycles have tightened in a way that was not previously operating. A system this compact, this tightly wound, does not need a large perturbation to produce a large response. It just needs a nudge. And something somewhere in that system has recently been nudged. Part 11. The accretion trap. To understand why the April 6th flare happened, you need to understand what Cygnus X-3 looks like in the time leading up to a giant flare, because the flare does not come from nowhere. It is the release of an accumulation, and the accumulation is visible in the data if you know what to look for. In the weeks and months before a giant radio flare, Cygnus X-3 typically enters what astronomers call a hypersoft state. The X-ray spectrum changes character. The thermal emission from the inner accretion disk becomes dominant, suggesting the disk has pushed inward, closer to the compact object, burning hotter and brighter in X-rays, and simultaneously the radio emission drops, essentially to nothing. The jets, which normally produce a continuous low-level radio signature, shut down. This jet quenching is the key to the pressure cooker. When the jets are active, they are carrying away energy and angular momentum from the inner disk system, providing a release valve for the energy being deposited by infalling matter. When the jets shut off, that release valve closes. Matter continues falling in from the Wolf-Rayet wind. The disk continues gaining energy from the accretion process, but nowhere for that energy to go except into the disk itself, which grows more and more turbulent, more magnetically active, more gravitationally stressed. The magnetic fields in the disk, which are thought to play a crucial role in launching jets, are reorganizing during this period, building up in strength and configuration toward the geometry required to relaunch the outflow. Think of it as a river being dammed. Upstream the water is still flowing, the Wolf-Rayet wind is still feeding the system, but the outflow has been blocked. The reservoir fills, the pressure builds, the dam does not hold indefinitely. What triggers the relaunch of the jet is not fully understood. Current models invoke some combination of magnetic field reconnection in the inner disk, a threshold instability in the disk itself, or a sudden change in the accretion rate that tips the system past a critical transition. What happens after the trigger is somewhat better understood. The jet reactivates. Plasma is expelled at relativistic velocities. The initial emission from the reactivated jet is optically thick, meaning it absorbs its own radiation and appears faint. As the jet expands and the plasma density drops, it becomes optically thin, and the synchrotron emission blazes into visibility across a wide range of radio frequencies simultaneously, producing the giant flare profile that Russian 600 recorded on April 6th. The question that the 2026 data forces on us is this: if the previous jet quenching and reactivation cycle took on the order of 200 days, what changed to compress it to 80? The accretion trap seems to be resetting faster, the pressure is building faster, or perhaps the threshold for triggering the jet reactivation has lowered. Either way, the internal dynamics of the disk and jet system have shifted in a way that the existing models, built on the slower historical cadence, do not naturally predict. Part 12. The sudden release. The moment of jet reactivation in a system like Cygnus X-3 is, by any measure, one of the most energetic events that occurs regularly in the Milky Way galaxy. The plasma that is ejected moves at a substantial fraction of the speed of light. In Cygnus X-3, the jets are observed to have apparent velocities that, due to projection effects when a jet is aimed partially toward the observer, can appear superluminal, faster than light. This is not a violation of physics. It is a geometric illusion produced when a jet moving at, say, 70 or 80%, the speed of light is pointed at an angle close to the line of sight. The component of the jet's motion toward the observer combines with the light travel time effect in a way that makes the apparent transverse motion exceed the speed of light in projected sky coordinates. It is a well-understood relativistic effect, but it is still startling to see in the data. The jet slams into the dense Wolf-Rayet stellar wind surrounding the binary system. That collision produces a shock wave, an interface where the fast jet plasma is decelerated and compressed by the ambient wind material. At this shock, the electrons in the plasma are accelerated to relativistic energies, and those relativistic electrons, spiraling around the magnetic field lines compressed at the shock, produce synchrotron radiation. This synchrotron emission is what we detect as the giant radio flare. It brightens rapidly as the shock expands and more emitting volume comes into play, peaks when the synchrotron emission is most efficient, and then fades as the shock dissipates and the electron population loses energy. The 6.6 Jansky peak brightness of the April 6th flare at 11.2 GHz represents the emission from a relativistic shock expanding into the Wolf-Rayet wind. The reason it is so bright enough to make Cygnus X-3 the brightest radio source in the galaxy, is a combination of factors: the power of the jet, the density of the wind medium enhancing the shock emission, and the geometry of the system relative to our line of sight. All three of these factors conspired to produce the observed flare amplitude, and all three are connected to the changing state of the system in 2026. Part 13. Why it gets so bright. The physics behind a 6 Jansky radio flare from an object 29,000 light-years away deserves a moment of genuine appreciation, because what is happening is extraordinary, even by the standards of compact object astrophysics. Synchrotron radiation is what happens when a charged particle, an electron in this case, moves through a magnetic field. The magnetic field curves the particle's path, and a charged particle moving on a curved path radiates energy. If the particle is moving at a significant fraction of the speed of light, the radiation is intense and collimated in the forward direction of the particle's motion, and its spectrum extends from radio wavelengths up through optical and X-ray frequencies depending on the particle's energy. In the jets of Cygnus X-3, the electrons are being accelerated to enormous energies by the jet launching mechanism and by the shock interaction with the Wolf-Rayet wind. The magnetic fields in the jet and at the shock interface are strong, perhaps millions of times stronger than the Earth's own magnetic field in the densest regions. The combination of energetic electrons and strong magnetic fields produces a synchrotron luminosity that, during a giant flare, temporarily exceeds the radio emission of virtually every other object in the galaxy. The Wolf-Rayet wind plays an amplifying role here. Because the wind is dense close to the binary system, the shock between the jet and the wind occurs in a region of high material density. A denser ambient medium means a stronger shock. A stronger shock means more efficient particle acceleration. More efficient particle acceleration means more synchrotron radiation. The companion star is, in a real sense, the fuel that makes the flares so optically violent. There is also a viewing angle effect. The compact object in Cygnus X-3 has its jets pointed at an angle of roughly 14 degrees from our line of sight. That is close to, but not perfectly aligned with the direction to Earth. At this angle, relativistic beaming, the same geometric effect that produces apparent superluminal motion, slightly amplifies the apparent brightness we observe compared to what a sideways observer would see. The system is not the intrinsically most powerful radio source in the galaxy, but our viewing angle makes it appear near the top during flare events. Each of these factors, jet power, wind density, shock physics, viewing geometry, can potentially change over time. And if the 2026 acceleration of flare activity reflects changes in one or more of these factors, the flares may not just be arriving faster, they may also be structured differently, carrying different information about the current state of the engine. That is something the multi-wavelength follow-up campaigns initiated after the April 6th detection are actively investigating right now. Part 14, the 2026 acceleration problem. Let me lay out the observational puzzle as cleanly as I can because the details matter here. In the historical record of Cygnus X-3 flare activity, the gaps between major events have been measured in months and sometimes years. The 2016 to 2017 activity period had flares separated by roughly 200 days. Before that, the 2011 event was relatively isolated. The system could go years between major outbursts. This slow, irregular cadence was difficult to predict, but broadly consistent with models where the accretion disk cycles through instability modes on long timescales, periodically building up enough stored energy to launch a giant jet event. The 2026 timeline breaks this pattern. January 2026, giant flare. February 2026, smaller intermediate flare event. April 6th, 2026, second giant flare. The total window from the first giant flare to the second is roughly 80 days, not 200 days, not a year, 80 days. Several hypotheses have been proposed to explain this compression. The most straightforward is an increase in the mass transfer rate from the Wolf-Rayet companion. If the stellar wind has intensified, more material is feeding the accretion disk per unit time, the disk fills faster, the instability threshold is reached sooner, and the jet is relaunched on a shorter cycle. This is physically plausible because Wolf-Rayet stars can undergo episodes of enhanced mass loss, and a star in the late stages of its evolution may be entering a more turbulent phase. A second hypothesis involves the disk instability model itself. The accretion disk around the compact object is not a simple, smooth structure. It is a turbulent, magnetized, radiation-driven environment that can develop its own internal instabilities independent of the mass supply rate. These instabilities, governed by the magnetorotational instability and other fluid dynamic processes, can have characteristic timescales that are sensitive to the disk's physical state. If something in the disk has changed, its density profile, its ionization state, its magnetic field configuration, the instability cycle could run faster without requiring a change in the external mass supply. A third possibility, less well developed in the current literature, is that the magnetic field geometry in the jet launching region has shifted into a configuration that lowers the energy threshold for jet reactivation. This would mean the system is not storing as much energy before each release, producing flares that are perhaps slightly less powerful on average, but arriving more frequently. The February mini-flare is potentially diagnostic here, because it suggests the system attempted a jet reactivation between the two giant flares, but did not fully commit to it. A failed or partial reactivation that released some energy, but left the disk still loaded enough to produce the April giant flare is consistent with an instability model, where the trigger threshold has become lower and more easily reached, but where the full release requires a secondary triggering condition that was only met in April. No consensus model yet explains all of these data points simultaneously. What the data clearly shows is that the 2026 behavior is outside the parameter space the models were built to describe. The system is not following its own historical precedents, and a system that is not following its historical precedents is, by definition, unpredictable. Part 15. The pattern that isn't a pattern. Here is the thing about Cygnus X-3 that most astronomy communicators underemphasize because it is less satisfying than a clean narrative. There is no periodic pattern to its giant flares. This is not unusual for accreting compact object systems. Many of them show irregular, chaotic variability that resists clean periodicity. but Cygnus X-3 is particularly emphatic about it. Attempts to find a repeating period in the giant flare timing have consistently failed. There is no oscillation, no clock, no reliable cadence. The system produces events when its internal conditions reach whatever threshold triggers jet reactivation, and those conditions are driven by a chaotic combination of mass transfer variability, disk physics, magnetic field evolution, and orbital dynamics. The result is irregular in the truest statistical sense. This irreducible unpredictability is part of why the 2026 acceleration is so striking. We cannot say with confidence whether the 80-day gap between the January and April flares represents a new short-period mode that will persist, or whether the next event will arrive in 40 days or in 2 years. The system is not giving us a new clock, it is giving us a new sample, and one sample is not a pattern. It is a data point, a troubling, interesting, and still unexplained data point in a record that already had no easy answers, and that irreducible uncertainty is paradoxically one of the most scientifically valuable things about Cygnus X-3. It cannot be ignored, it cannot be filed and forgotten, it demands continued monitoring, continued modelling, continued confrontation with the limits of what the current physics can explain. And right now, in the months following April 6th, 2026, those limits are being tested more urgently than they have been in years. Part 16. ULX Revelation. In 2024, the Imaging X-ray Polarimetry Explorer delivered a result that reframed how astrophysicists think about an entire class of objects, and Cygnus X-3 was central to it. Ultraluminous X-ray sources, ULXS, are point sources of X-ray emission found in other galaxies, typically in star-forming regions, that appear to radiate at luminosities far exceeding what the standard physics of accreting neutron stars and stellar mass black holes should permit. There is a theoretical limit, called the Eddington luminosity, at which the radiation pressure from an accreting object exactly balances the gravitational force pulling matter inward. Exceed this limit, and the radiation should blow away the infalling material, shutting down the accretion. ULXs appear to blow past this limit by factors of 10, 100, or more. For decades, the dominant explanation for ULXs involved intermediate mass black holes, objects with masses of thousands to tens of thousands of solar masses that would have a naturally higher Eddington luminosity. A bigger mass means a bigger Eddington limit, and if ULXS are simply more massive than expected, the observed luminosities are no longer impossible. The problem is that no other evidence for abundant intermediate mass black holes had been convincingly established. The IXPE analysis of Cygnus X-3 combined with observations of known ULXs suggested a different explanation. The accretion disk under conditions of high mass transfer rates can develop a funnel-shaped inner region where the radiation is collimated, preferentially beamed outward along the axis of the disk, perpendicular to the disk plane. An observer looking down the funnel sees a much higher apparent luminosity than the true isotropic luminosity of the source. The system is not actually violating the Eddington limit. It is redirecting its emission into a cone and appearing artificially bright to anyone positioned inside that cone. Cygnus X-3, viewed at 14 degrees from the jet axis, is essentially looking almost directly down the funnel. Our line of sight is nearly aligned with the collimated output. This means the X-ray luminosity we observe is enhanced by this beaming effect, placing Cygnus X-3 in the same apparent luminosity range as distant ULXs in other galaxies. It is not that Cygnus X-3 is impossibly bright. It is that we are watching it from an angle that makes it look impossibly bright. The implication for the 2026 story is this: when the system's state changes, when the flares arrive faster, and the accretion disk reconfigures, the funnel geometry may also change. The beaming factor may shift. What we observe as changing brightness during flare events is partly real, and partly a projection effect that varies with the inner disk geometry. Understanding this distinction is crucial for interpreting whether the 2026 flares represent more total energy output from the system, or simply a different geometric configuration that changes how much of that energy is directed toward Earth. Part 17. Pivatron Discovery. The LHAASO detection of peta-electron-volt gamma-ray emission from the direction of Cygnus X-3, confirmed in 2025, placed this already extreme system in a category that, until recently, astrophysicists would not have considered possible for a stellar mass binary. To put a peta-electron-volt in context, 1 peta-electron-volt is 10 to the 15th power electron-volts of energy. The Large Hadron Collider at CERN, the most powerful particle accelerator humans have ever built, reaches collision energies of about 14 tera-electron-volts, which is 14 times 10 to the 12th power electron-volts. A peta-electron-volt is roughly 70 times the LHC's maximum collision energy. When LHAASO detected emission at these energies from the direction of Cygnus X-3, it meant that something in or near that system was accelerating particles to energies that dwarf our most powerful machines. The critical evidence linking the peta-electron-volt emission to Cygnus X-3 specifically, rather than to some unrelated background source in the same direction, is the orbital modulation. The intensity of the very high-energy gamma-ray emission varies in sync with the 4.8-hour orbital period of the binary system. This modulation is the astrophysical equivalent of a fingerprint. Background sources do not produce signals modulated on the specific orbital period of a foreground binary system. The peta-electron-volt emission is coming from inside Cygnus X-3, or from plasma directly associated with its jets interacting with the surrounding wind. The mechanism most likely responsible is hadronic acceleration in the relativistic jets. When the jet plasma contains protons, as is likely for a powerful microquasar jet, those protons can be accelerated to extreme energies by the electric fields associated with the relativistic shock. Protons accelerated to peta-electron-volt energies that then interact with ambient matter, and radiation fields produce the secondary gamma rays and neutrinos observed at the highest energies. The jets of Cygnus X-3 are, in effect, a natural particle accelerator of a scale and power that no human engineering has approached. This connects directly to the 2026 flare acceleration because the peta-electron-volt emission varies with jet activity. During giant flare events, when the jet power is at its maximum, the particle acceleration to the highest energies should also be at its maximum. If the flares are now arriving more frequently, there are more periods of maximum power jet activity, and more windows during which Cygnus X-3 is operating as the galaxy's most powerful natural particle accelerator. Whether the LHAASO detection rate is correspondingly increasing is one of the open questions that the ongoing multi-wavelength campaigns are tracking. Part 18. Neutrino Prediction. The hadronic model for peta-electron-volt emission from Cygnus X-3 makes a prediction that has not yet been confirmed but would, if confirmed, transform our understanding of this system. When protons accelerated to peta-electron-volt energies interact with surrounding matter or radiation fields, they produce pions, elementary particles that decay into gamma rays and also into neutrinos. Neutrinos are ghostly particles that interact with matter only through the weak nuclear force, which means they pass through virtually everything. They travel from their source to Earth without being absorbed, scattered, or deflected. A neutrino detection from the direction of Cygnus X-3, timed to coincide with a giant radio flare, would be direct evidence of hadronic jet physics operating in this system, and it would provide information about the jet composition and energy content that is inaccessible through any other channel. The IceCube Neutrino Observatory at the South Pole, a cubic kilometre of Antarctic ice instrumented with light detectors, has been searching for neutrino emission from Cygnus X-3 for years without a definitive detection. The challenge is sensitivity. The expected neutrino flux, given the observed gamma-ray luminosity and reasonable assumptions about the hadronic fraction of the jet, is close to but possibly below IceCube's current detection threshold for a source at 29,000 light-years distance. Planned next-generation detectors including IceCube Gen 2, a 10 cubic kilometre expansion of the existing array, and KM3NET, a similar instrument being deployed in the Mediterranean Sea, will push the sensitivity threshold significantly lower. If the theoretical predictions are correct, these instruments should be capable of detecting neutrino emission from Cygnus X-3, particularly during the intense giant flare events like those in January and April 2026. Each giant flare is a window of opportunity, and with the flares now apparently arriving more frequently, the statistical chances of a coincident detection with a sensitive enough instrument improve accordingly. Part 19. Jet Physics Problem. The jets of Cygnus X-3 are among the most studied and least understood features of the system, and the difficulty of understanding them reflects a fundamental gap in compact object astrophysics that extends far beyond this single source. Two theoretical models for jet launching have dominated the field for decades. The Blandford-Znajek mechanism proposes that the rotational energy of the spinning compact object, a black hole spinning at high rates, threads the magnetic field lines of the accretion disk through the black hole's ergosphere, an external region where space-time is dragged in the direction of the black hole's rotation. This electromagnetic interaction extracts rotational energy from the black hole and channels it into the jets. The Blandford-Payne mechanism proposes instead that the jets are launched by magnetic fields anchored in the rotating accretion disk itself, which act like a centrifugal pump to fling material outward along the field lines perpendicular to the disk plane. Both mechanisms require strong, ordered magnetic fields threading the inner accretion disk. Both predict that jet power should be related to the accretion rate and the magnetic field strength. But the precise relationship, the efficiency of energy extraction, the conditions under which jets are launched versus quenched, and the structure of the jet close to its launch point remain active research problems. The gap between the theoretical models and the observational constraints is large enough to accommodate very different physical scenarios, and Cygnus X-3 has been frustratingly ambiguous in distinguishing between them. The jet quenching observed before giant flares, the hypersoft state, is itself a clue that has not been fully decoded. If jets are quenched when the accretion rate is high, as seems to be the case in Cygnus X-3, that seems counterintuitive for models where higher accretion should produce more jet power. The resolution may involve the disk geometry changing at high accretion rates in a way that disrupts the ordered magnetic field configuration needed for jet launching. But this is an idea still being developed, not a settled explanation. Understanding jet physics in Cygnus X-3 matters for the 2026 story, because the change in flare cadence must ultimately be explained in terms of change conditions in the jet launching region. Whether that means a change in the accretion rate, a change in the magnetic field configuration, or a change in the spin energy extraction efficiency depends on which jet mechanism is operating. And because we do not yet know which mechanism dominates, we cannot yet specify what exactly has changed to produce the faster flares. Part 20. Alignment factor. One final piece of the observational puzzle deserves mention, because it slightly modifies how we should interpret the apparent drama of the 2026 detections. The jets of Cygnus X-3 are oriented at roughly 14 degrees to our line of sight. They are not pointed directly at us, which would require us to be looking straight down the barrel of the jet. But they are much more closely aligned with our line of sight than a randomly oriented jet would be. A random orientation in three-dimensional space would most likely produce a jet angle of 45 to 90 degrees from the line of sight. 14 degrees is unusually well aligned with Earth. This alignment matters for observations because of relativistic beaming. When a source is moving toward the observer at a significant fraction of the speed of light, its emission is Doppler boosted and collimated in the forward direction. The approaching jet in Cygnus X-3 is brighter, in our observations, than it would appear to an observer positioned at 90 degrees to the jet axis. The receding jet moving away from us is dimmed by the same effect. The net result is that we see a brighter flare than the system's intrinsic power alone would predict for an observer at a different location in the galaxy. This does not mean the flares are less physically significant. The energy is real, the jet is real, the acceleration in flare cadence is real. But the impression of an extreme change in brightness may be slightly amplified by our favourable viewing geometry. A hypothetical observer positioned 90 degrees from the jet axis would see the same events as less bright and might find them less visually dramatic in the data. What it should not do is diminish the core fact that remains true regardless of viewing angle. The flares are arriving faster, the system is in a different behavioural state than it was a decade ago, and the physics driving that change is not yet understood. The geometry makes the signal louder. The mystery makes it matter. Part 21. Phone Frequency Myth. When the April 6th detection circulated beyond the astronomy community and reached general social media and science news platforms, a particular framing took hold rapidly. The signal arrived at the same frequency as your phone. The implication, sometimes stated directly and sometimes left for the imagination, was that this should be alarming in some personally resonant way. That the universe was somehow reaching into the frequencies of your daily life. That the boundary between cosmic and intimate had been crossed. It is worth unpacking exactly what is true and what is misleading about this framing, because the truth is interesting, and the misleading part actively obscures what is genuinely important about the story. The frequency overlap is real. 4.7 to 30 GHz spans the operating range of Wi-Fi, most modern cellular bands including 5G, satellite communication systems, and radar. These frequencies are used by human technology because the Earth's atmosphere has a window of relatively low absorption in this range. Radio waves at these frequencies pass through the atmosphere without being significantly attenuated, which makes them practical for both ground-to-ground and space-to-ground communication. Engineers building communication systems naturally exploited this window, and they were not wrong to do so. Astrophysical sources also emit at these frequencies for completely unrelated physical reasons. Synchrotron radiation from relativistic electrons spans a very broad range of frequencies, and the particular part of that range that is most intense depends on the electron energies and magnetic field strengths involved. In Cygnus X-3, during a giant flare, the conditions happen to produce peak synchrotron emission in the range that overlaps with telecommunications frequencies. This is a coincidence of physics, not a connection of intent. The signal strength at Earth is also important to grasp. 6.6 Jansky sounds large if you have no reference point, but a Jansky is 10 to the negative 26 watts per square meter per hertz. At 6.6 Jansky across a narrow frequency band, the total radio power intercepted by, say, a square meter of collecting area at Earth is on the order of 10 to the minus 24 watts. Your phone transmits at roughly 1/10 of a watt to communicate with cell towers. The cosmic signal intercepted by your entire body is roughly 23 orders of magnitude weaker than your phone's own transmission. Your phone would not notice the signal from Cygnus X-3 if you held it outside all night. The universe is not calling you back. What the phone frequency framing does, in a subtle but meaningful way, is redirect attention from the real alarm, which is the changing behaviour of an extreme and poorly understood astrophysical system, toward a false alarm rooted in frequency coincidence. The story that matters here is not that the signal shares a frequency band with your phone. The story that matters is that the signal is arriving more often from a system we cannot fully explain, and that the acceleration is telling us something important about physics at the edge of our understanding. That story is harder to explain than frequency coincidence, but it is also vastly more interesting. Part 22. Biology and Schumann Claims. Some discussions of the April 6 detection drifted into territory involving the Schumann resonances, which are electromagnetic resonances of the Earth ionosphere system, driven by global lightning activity. The Schumann resonances occur at extremely low frequencies, roughly 7.8, 14, 20, and 26 Hz, not gigahertz, Hertz. The Cygnus X-3 flare frequencies are roughly 1 billion times higher in frequency than the Schumann resonances. These are not the same phenomenon. They do not interact. They do not reinforce each other. The Schumann resonances are a real physical feature of the Earth system with a well-understood origin and well-characterized properties. Claims that the cosmic radio flare at gigahertz frequencies somehow influenced or amplified Schumann resonances, or that the combination produced biological effects, have no physical basis. The signal strength of the cosmic flare at Earth's surface is incomparably below the energy levels of natural terrestrial electromagnetic phenomena, including the Schumann resonances themselves. The actual story of Cygnus X-3's 2026 behaviour does not need embellishment from terrestrial biological claims. A system potentially entering a new high-activity state, 2 giant flares in 80 days, peta-electron volt particle acceleration, unresolved compact object identity after 60 years. The real science is already remarkable enough to carry the story without adding layers that the physics does not support. Part 23. Pattern Seeking in Astronomy. Human beings are pattern recognition machines, and that cognitive trait is simultaneously the foundation of scientific reasoning and its most persistent source of error. When we look at a system that has produced multiple radio flares, we naturally want to find the period, the clock, the rule that determines when the next one will come. This impulse is not irrational. Many astrophysical systems do have periodic behaviours. Binary stars eclipse each other on regular schedules. Pulsars rotate with extraordinary precision. Some accreting systems show quasi-periodic oscillations in their X-ray-like curves. The universe does genuinely contain clocks. Cygnus X-3 is not a clock. Its giant flare timing has no reliable period. The same system that produced 2 major events separated by 200 days in 2016 to 2017 went years without a comparable event before the 2026 activity began. The pattern-seeking impulse looks at the January and April flares, calculates an 80-day period, and wants to predict the next event. But the data do not support that prediction. The system's behaviour is chaotic in the technical mathematical sense, driven by non-linear processes that are sensitive to initial conditions in ways that make long-term forecasting impossible with current models. What the 2026 data does seem to show is a real acceleration in the activity level, not necessarily a new period, but a genuine change in the statistical distribution of waiting times between events. That is a scientifically meaningful observation. It tells us the system is operating in a different regime than before, but it does not give us a calendar, and mistaking a change in activity level for a new predictable clock would be exactly the kind of pattern-seeking error that leads to confident but wrong scientific predictions. The real pattern in the Cygnus X-3 data, the one that is both genuine and poorly explained, is that something about the underlying physics has shifted. Not when the next flare will arrive, that the next flare will likely arrive sooner than historical precedent would have predicted. That distinction matters, and it is what the community is now trying to quantify and explain. Part 24. Real danger or not. Let me be completely direct about the hazard question, because it surfaces in almost every popular treatment of high-energy astrophysical transients, and the answer deserves to be delivered without ambiguity. The radio flare from Cygnus X-3 on April 6, 2026, poses no hazard to Earth or to any living thing on it. The signal strength at Earth's surface is too low by many orders of magnitude to interact with any biological or technological system in a meaningful way. The 29,000 light-years of distance has done its job. The inverse square law, which governs how electromagnetic energy spreads across space, has reduced the originally powerful emission to a whisper that requires a 576-metre ring telescope to detect at all. Radio waves in the gigahertz range are also non-ionizing radiation. They do not carry enough energy per photon to break chemical bonds, disrupt DNA, or damage cellular structures. The biological hazards associated with high-energy radiation, like X-rays and gamma rays, do not apply to radio waves of any intensity that exist naturally on Earth from cosmic sources. The same frequencies used in Wi-Fi and cellular communication are in your environment at intensities millions of times higher than the cosmic signal, and decades of biological research have not established a harmful mechanism at those power levels. The genuinely extreme aspects of Cygnus X-3, the relativistic jets, the peta-electron-volt particle acceleration, the ULX-class X-ray emission, are real and extraordinary, but they are confined to the immediate vicinity of the system. The dangerous particle radiation and X-ray emission are absorbed and scattered long before reaching Earth. What arrives here is radio waves, quiet, cold, energetically negligible radio waves that require specialized scientific instruments to detect. The real danger in this story is not physical, it is epistemic. A system we do not understand is changing in ways we did not predict. That is not a threat to human health, but it is a challenge to human knowledge, and that challenge is not one we can afford to ignore. The fact that we cannot explain the 2026 flare acceleration, that our best models of accretion disk physics and jet launching do not account for it, means there is something operating in this system that our current framework does not capture. What we do not understand in one context, we cannot apply correctly in related contexts. That gap in understanding has real consequences for how accurately we model compact object physics across the galaxy. Part 25. Psychological impact. There is something specific that happens in the mind when it genuinely grasps that the signal detected on April 6, 2026, left its source when humans were painting Chauvet Cave, and I want to spend a moment on what that something is, because it tells us something important about why Cygnus X-3 generates the kind of reaction it does, even among people with no background in astrophysics. The human brain was not built for cosmological timescales. Its intuitive time sense operates over a range from seconds to decades. Centuries are abstract. Millennia are barely comprehensible. 29,000 years is a number so far outside the range of intuitive experience that the mind cannot really grasp it as time. It becomes more like a quantity than a duration, more like a very large number than a felt span of lived experience. But the mind does something interesting when it is presented with that gap. It feels the mismatch. It senses the uncanniness of a signal that outlasted every human civilization, every language, every nation, every religion, every technology, everything we have ever made or thought or been, and arrived, still carrying information, at a machine built by people who had no idea it was coming. The discomfort is not irrational. It is the correct emotional response to a genuine cognitive confrontation with scale. This is why the story of Cygnus X-3, and the story of the April 6th flare specifically, carries a weight that purely technical descriptions do not capture. The science is extraordinary in its own right, but the temporal dimension adds something that the science alone cannot add. A visceral reminder of how small the human frame of reference is relative to the universe in which it exists. And that reminder is not comfortable, but it is valuable. The scientific uncertainty mirrors the psychological discomfort. We cannot know Cygnus X-3 as it is now. We can only know it as it was 29,000 years ago, and even that ancient snapshot refuses to yield a complete explanation. The system is changing, but we are receiving the news with a 29,000-year delay. The urgency we feel about understanding it coexists with a fundamental impossibility of contemporaneous knowledge, and that combination, urgency plus impossibility, is perhaps the most honest description of what it feels like to do astronomy at the edge of the galaxy. Part 26. Death of the Wolf-Rayet star. Everything we have discussed so far, the flares, the jets, the accretion disk instabilities, the peta-electron-volt particle acceleration, all of it is happening in the context of a system that is headed somewhere. And I want you to sit with that for a moment, because it changes the way the whole story feels. We have been talking about Cygnus X-3 as though it is a fixed object. a permanent fixture in the sky that we point telescopes at, collect data from, argue about in papers, and file away for the next generation of researchers to argue about some more. But it is not fixed. It is not permanent. It is a system in motion, evolving on timescales that dwarf anything in human experience. And what we're watching in 2026, these faster flares, this restless behaviour, this acceleration that our models cannot explain, may not be random noise. It may be a signal from inside the machine, a sign that something fundamental is changing, not just in the accretion disk, not just in the jet-launching geometry, but in the star itself. Not in the short term, not on human timescales, but in the medium astronomical term, which is short by galactic standards. The Wolf-Rayet companion star in Cygnus X-3 is not going to be a Wolf-Rayet star forever. It is going to die. And the question that the 2026 data quietly raises, the one that none of the official alerts say out loud but that sits underneath all of them, is whether we might be watching the very early, subtle, nearly undetectable beginning of that process right now. Let me explain what a Wolf-Rayet star actually is, because the name does not do it justice. These are not ordinary massive stars. They are what you get after an ordinary massive star, something born with perhaps 50 times the mass of our Sun, has already burned through its entire hydrogen supply and stripped itself nearly bare. Most stars spend the bulk of their lives fusing hydrogen into helium in their cores. Our Sun has been doing this for about 4.5 billion years and has roughly another 5 billion years of hydrogen left. A star 50 times more massive burns through that same fuel supply in a few million years, not billions, millions. It is not that the star is inefficient. It is that the scale of energy demand at that mass is so extreme that the fuel simply does not last. After the hydrogen is gone, the star moves on to helium, then carbon, then oxygen, then neon, then silicon, each stage faster than the last, each stage more thermodynamically demanding, each stage producing a core that is hotter and denser and more unstable than the one before. The radiation pressure from all that burning becomes so intense that the star literally cannot hold on to its outer layers. They are blown away in a continuous ferocious stellar wind, not gently, not gradually in the way we think of stellar evolution, but aggressively, at speeds of thousands of kilometers per second, shedding mass at a rate that would drain the entire Sun in roughly 1 million years. What is left after all that mass loss is what we call a Wolf-Rayet star, a hot, exposed stellar core, blazing at surface temperatures between 50,000 and 100,000 Kelvin. Compare that to our Sun's roughly 6,000 Kelvin, with no hydrogen envelope left at all. Just the naked, luminous, violently active interior of a star that has burned through most of its biography and is now in its final chapter. And in Cygnus X-3, this star is orbiting a compact object, either a black hole or a neutron star, we genuinely still do not know which, at a separation of just a few solar radii, completing a full orbit every 4.8 hours. The compact object sits inside the Wolf-Rayet stellar wind, constantly bathed in the outflowing material, accreting what it can, powering X-ray emission, and jets from what it captures. The entire system is extraordinarily tightly coupled. What the star does, the compact object feels immediately. There is almost no buffer, almost no damping between the two. Now here is where the death clock comes in. When the Wolf-Rayet's core finally runs out of fuel to fuse, and it will, on a timescale measured in tens of thousands to hundreds of thousands of years from now, which is cosmologically soon, even if it is incomprehensibly far from any human perspective, the collapse happens fast. For a star of this mass, the core collapses not over years or centuries but over seconds, literally seconds. The outer layers, suddenly unsupported by the outward pressure of nuclear burning, fall inward at a significant fraction of the speed of sound in dense stellar material, slam into the increasingly rigid core and bounce. That bounce produces one of two outcomes. Either a supernova explosion of almost incomprehensible energy, We're talking about more energy released in a few seconds than our Sun will emit over its entire 10 billion year lifetime. Or, at the high mass end, possibly a direct collapse straight into a black hole, with no bright explosion at all. Just a star, and then not a star. The uncertainty about which pathway this particular system will follow reflects our still incomplete understanding of massive star physics at these extreme mass ranges. We do not yet have a reliable model that tells us, for a star of this specific mass and composition, which way the coin falls. The timescale is uncertain. Tens of thousands of years is the lower bound. Hundreds of thousands of years is plausible. Either way, it is not something we will observe. No human civilization, and quite possibly no descendant of human civilization, will be watching when it happens. By the time that event occurs, the photons carrying the news will spend another 29,000 years in transit before reaching wherever Earth happens to be. But here is the part that connects back to 2026, and to the faster flares, and to the thing that nobody can fully explain yet. Before the final collapse, the mass loss from a Wolf-Rayet star does not stay steady. It gets erratic. As the star moves through its final nuclear burning stages, as the internal structure of the core changes, as the pressure and temperature gradients shift, the stellar wind can go through episodes of intensification. Bursts of enhanced mass loss, periods where more material is ejected more rapidly, brief phases where the wind density increases significantly before settling back down. These episodes are not perfectly understood, but they are observed in Wolf-Rayet stars across the galaxy. They are part of the expected late-stage behavior of a star approaching its end. And in a system as tightly coupled as Cygnus X-3, an increase in the Wolf-Rayet's mass loss rate would feed directly into the accretion disk of the compact object. More material flowing inward, the disk filling faster, the instability threshold reached sooner, the jet reactivating on a shorter cycle, giant flares arriving not every 200 days, as they did in the historical record, but every 80 days. With smaller events in between, as the system attempts partial releases before the full discharge. Do you see where this is going? The 2026 flare acceleration may not be a random fluctuation in the accretion disk. It may not be a quirk of the magnetic field geometry, or a coincidental shift in the jet launching conditions. It may be the compact object responding, in the only language it has, which is matter and energy, and jets of relativistic plasma, to a change in its companion star. The compact object is reading the Wolf-Rayet's death clock, and the clock may have recently ticked a little faster. This is not a confirmed hypothesis. There is no consensus in the literature that the 2026 activity is driven by a change in the stellar wind rather than by something internal to the disk. The data does not yet distinguish cleanly between these possibilities, but the hypothesis is physically coherent, observationally motivated, and carries with it a genuinely strange implication, that the unusual behavior we are seeing right now in our telescopes, in our data streams, in the alerts going out over the astronomers' telegram network, is the faint, distant, 29,000-year delayed echo of a dying star entering a new phase of its death. The flares are not just astrophysical curiosities. They may be a message from inside the machine, a message that has been travelling since before the first human city existed, arriving now in a world sophisticated enough to detect it, but not yet fully equipped to read it. The compact object at the centre of Cygnus X-3 is surrounded by a star that is burning toward its end. And as that star changes, slowly, on timescales, we will never directly observe. The compact object tells us about those changes the only way it can. It fires its jets, it produces its flares, it gets louder, and we, 29,000 light-years away, with our ring-shaped telescope in the Caucasus Mountains, are just barely starting to understand what we are hearing. Part 27. Aftermath Scenarios. What happens to the Cygnus X-3 system after the Wolf-Rayet star's death depends on details that we cannot yet determine with certainty, and the possible outcomes span a remarkable range. Not just a little remarkable. We're talking about futures so different from one another that they almost feel like they belong to completely separate stories. The same system, the same two objects racing around each other every 4.8 hours in a space smaller than the Sun, could end up becoming one of three completely different things. And which path it takes depends on physics happening deep inside a stellar core that we cannot see, at densities we cannot replicate, on timescales we will never observe directly. Let me take you through each one, because they are each worth understanding on their own terms. The first possibility is the one that, if you have been following gravitational wave astronomy over the past decade, will immediately feel familiar. If the Wolf-Rayet star collapses directly into a black hole, skipping the bright supernova explosion entirely and just quietly ceasing to exist as a star and becoming a compact remnant in a matter of seconds, and if that collapse is symmetric enough that the gravitational jolt does not kick the two objects apart, then what you are left with is two black holes, orbiting each other, in an already extraordinarily tight binary system. Think about what that means for a moment. Right now, Cygnus X-3 contains one compact object, either a black hole or a neutron star, we do not know which, and one Wolf-Rayet star, both of them fitting within a volume comparable to the size of our Sun. Replace the Wolf-Rayet star with a second compact object, and you now have a double black hole binary, two of the most extreme objects in the universe, locked in the same tiny orbital embrace that the current system already occupies. No stellar wind anymore, no accretion disk, no jets, no radio flares, just two black holes circling in silence. And here is the thing about two black holes circling each other. They do not stay that way forever. According to general relativity, any two massive objects in orbit around each other emit gravitational waves, ripples in the fabric of space-time itself, propagating outward at the speed of light. Those waves carry energy, and as the system loses energy to gravitational wave emission, the orbit shrinks. Slowly at first, imperceptibly slowly over human timescales, but relentlessly over astronomical ones. The two black holes spiral inward, closer and closer, the orbital period shortening, the gravitational wave emission intensifying as the separation decreases, until eventually, after billions of years of this patient in spiral, they merge in a violent, catastrophic collision that releases more energy in gravitational waves in a fraction of a second than the Sun will emit in light over its entire lifetime. That merger would be detectable by LIGO-class instruments. Not just detectable, it would be one of the loudest gravitational wave events in the observable universe at the moment it occurred, visible to gravitational wave detectors across cosmological distances. Cygnus X-3, under this scenario, is not just an interesting binary system we happen to be watching in 2026. It is a gravitational wave source in formation. The radio flares we are detecting right now are, in a sense, the early biography of a system whose final chapter will be written in distorted space-time billions of years from now. That is scenario 1. Two black holes, a billion-year in spiral, a merger that shakes the geometry of space itself. Scenario 2 is less tidy, and in some ways more dramatic in the immediate term. When a massive star explodes as a supernova, rather than collapsing directly and quietly, the explosion is not perfectly symmetric. It cannot be. The collapsing core produces an asymmetric burst of neutrinos, those ghostly, nearly massless particles that carry away an enormous fraction of the gravitational energy released in the collapse, and the ejector from the explosion itself is not distributed evenly in all directions. The net result is a kick, a recoil, the newly formed compact remnant, where the neutron star or black hole gets shoved in some direction by the asymmetric forces of its own violent birth. These kicks are real. We know they are real because we observe isolated pulsars, neutron stars spinning and emitting radio beams like cosmic lighthouses, moving through the galaxy at velocities of hundreds of kilometers per second. Velocities that make no sense unless those objects were kicked out of their birth environments by exactly this mechanism. The kick is the literal recoil of a stellar explosion. Now apply that to Cygnus X-3. The Wolf-Rayet star explodes, the core collapses, a kick is imparted to the newborn compact remnant, and if that kick is large enough, if it exceeds the orbital velocity that was binding the two objects together, the binary system simply ceases to exist. The two objects fly apart. The compact object that was already there, the one producing the jets and the flares, goes one way. The newly born neutron star or black hole goes the other. Both become solitary runaway compact objects, hurtling through the galaxy at high velocity, carrying with them no trace of the extraordinary binary system they used to inhabit. This would be, from a purely observational standpoint, a loss. Not a loss anyone would be around to witness, but a loss in the sense that a remarkable and scientifically productive system would simply dissolve. The radio flares would stop. The jets would have nothing to power them. The accretion disk would have no companion star feeding it. Silence, where there was once the brightest radio source in the Milky Way. Whether Cygnus X-3 survives the supernova of its companion is genuinely uncertain. The probability is not negligible in either direction. Systems do survive companion supernovae. We have observational evidence of post-supernova binaries throughout the galaxy. But systems also get disrupted. The outcome depends on the kick velocity, the mass lost in the explosion, and the orbital geometry at the moment of collapse, all of which are parameters we cannot measure in advance with sufficient precision to make a confident prediction. The third scenario is the one that connects most directly to the history of gravitational wave astronomy, and it has a certain elegance to it. If the Wolf-Rayet star at the moment of its collapse has shed enough mass through its stellar wind that what remains is in the right range, not too heavy to form a black hole directly, but massive enough to produce a stable compact remnant, it may form a neutron star. A city-sized object with the mass of roughly 1 to 2 suns, spinning rapidly, threaded with magnetic fields of extraordinary strength, the remnant of a star that was once perhaps 30 or 40 times the mass of our Sun compressed into a sphere roughly 20 kilometers across. And if the binary survives the kick from that neutron star's formation, what you're left with is a double compact object system. Two extraordinarily dense objects, one whatever Cygnus X-3's current compact object is, and one freshly minted neutron star, orbiting each other in a tiny, tight binary. The radio flares would be gone. The Wolf-Rayet wind feeding the accretion disk would be gone. But what you would have instead is something that physicists have been fascinated by since the 1970s. In 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar, a system containing two neutron stars in a tight orbit, one of them pulsing like a radio clock with extraordinary regularity. By timing those pulses over years and decades, they were able to measure the orbital decay of the system with extraordinary precision. The orbit was shrinking. The two neutron stars were slowly spiraling together, and the rate of that in spiral matched exactly the predictions of general relativity for a system losing energy to gravitational wave emission. It was the first indirect proof that gravitational waves exist, and it earned Hulse and Taylor the Nobel Prize in Physics in 1993. A post-supernova Cygnus X-3, if it forms a double compact object binary and survives intact, would be a system of exactly that type, evolving toward merger over billions of years, potentially producing extraordinary phenomena in its earlier life, a rapidly spinning neutron star whose magnetic field could reach magnetar-class strengths, possibly producing bursts of hard X-rays, or even contributing to the population of gamma-ray bursts that we detect from across the universe. Each of these three outcomes is physically plausible. Each would produce a completely different future for the Cygnus X-3 system, and the uncertainty about which will occur directly mirrors the uncertainty we've been living with throughout this entire story. The uncertainty about what the compact object already inside Cygnus X-3 actually is. We do not know what is in that system right now. We cannot yet reliably predict what it will become. What we do know is that the 2026 flares are happening inside a system with a finite future, a companion star that is burning toward its end, a compact object that is reading that star's death in real time and translating it into jets and flares and radio signals that travel 29,000 years to reach us. Whatever Cygnus X-3 is becoming, it is becoming it right now, slowly, invisibly, at the edge of our understanding, and the signal, as always, is still arriving. Part 28. Gravitational Wave Future. The connection between Cygnus X-3 and the gravitational wave astronomy that LIGO and Virgo have opened up over the past decade is more than speculative. It is, when you follow the thread all the way to its end, one of the most quietly profound connections in modern astrophysics. And I want to spend some time on it, because I think it reframes everything we've been talking about in a way that makes the 2026 flares feel less like an isolated curiosity and more like a single frame from an extraordinarily long film. Let me start with what LIGO actually detects, because it is worth being precise about this. When the Laser Interferometer Gravitational Wave Observatory in Louisiana, or its twin in Washington State, or the Virgo detector in Italy, registers a gravitational wave event, what is physically happening is this. Two arms of a laser interferometer, each several kilometers long, are being stretched and compressed by an amount smaller than 1/10,000th the diameter of a proton. That is the signal. That is what billions of dollars of engineering and decades of experimental physics were built to detect. A displacement so small that describing it in meters requires a number with more than 20 zeros after the decimal point. And yet the instruments find it, reliably, because the physics of laser interferometry at that scale is now understood well enough to pull that signal out of the noise. The source of that signal is always the same category of event. Two massive compact objects, black holes, neutron stars, or one of each, that have been spiraling toward each other for an enormous span of time and have finally, in the last fractions of a second before merger, reached the point where the gravitational wave emission is powerful enough to reach us across cosmological distances. The merger itself is over almost instantly. The inspiral that preceded it took billions of years. Now here is the question that gravitational wave astronomers have been working on since the first detection in 2015. Where did those merging objects come from? How did two black holes, or two neutron stars, end up in the same tiny volume of space, close enough to merge within the age of the universe? The answer, for the majority of detected events, involves a pathway that looks something like Cygnus X-3. It starts with two massive stars born together in the same molecular cloud, orbiting each other in a wide binary system. Over millions of years they evolve. The more massive one exhausts its fuel first, expands, transfers mass to its companion, and eventually collapses into a compact object. The system may or may not survive that first collapse, depending on the supernova kick we discussed earlier. If it survives, you now have a compact object orbiting a still-living massive star. The massive star continues to evolve, loses mass through stellar winds, eventually itself collapses into a compact object. If the system survives that second collapse too, you have a double compact object binary. Two black holes, or two neutron stars, or one of each in a tight orbit. And then, over billions of years, gravitational wave emission slowly drains the orbital energy, the separation decreases, the inspiral accelerates, and eventually they merge. That pathway, two massive stars, two collapses, a long inspiral, a final merger, is the standard formation channel for the events LIGO detects. And Cygnus X-3 is sitting right in the middle of it. Not at the beginning, where you have two ordinary massive stars in a wide orbit, not at the end, where you have two compact objects spiraling together. Right in the middle, one compact object already formed, one massive star, the Wolf-Rayet companion, still alive, still evolving, still feeding matter into the accretion disk, still producing the jets and the flares and the radio signals that we are detecting in 2026. Systems like Cygnus X-3 are the progenitors of the compact binary mergers that LIGO detects. The black hole mergers and neutron star mergers that have been registering in those interferometers since 2015 did not form as isolated objects. They formed in binary systems. They went through phases that looked like what Cygnus X-3 looks like today. They produced jets, possibly. They produced radio flares, possibly. They were studied by whatever astronomers existed at the time, if any. And then the Wolf-Rayet companion died. The system survived or did not. And if it survived, the long, slow in-spiral began. The timescale mismatch between where Cygnus X-3 is now and where our LIGO source is at the moment of detection is enormous. Gravitational wave-driven in spiral from the orbital separations typical of a post-supernova compact binary, separations measured in astronomical units rather than the few solar radii of the current Cygnus X-3 orbit, takes billions of years. The Earth itself is only 4.5 billion years old. The universe is only 13.8 billion years old. We're talking about a process that consumes a significant fraction of the entire age of the cosmos. No human observation program will witness the merger of whatever Cygnus X-3 becomes. No successor civilization, no matter how long-lived, is likely to still be watching when that merger happens, because the merger will not happen on any timescale that resembles a civilization's lifespan. It is not that we will miss it because our telescopes are not good enough. It is that the event is scheduled in the loosest possible sense for a future so remote that the concept of missing it almost does not apply. And yet, and this is the part I find genuinely remarkable, understanding Cygnus X-3 today is directly relevant to understanding the LIGO detections happening right now. Not in a vague, everything is connected way. In a specific, quantitative, scientifically consequential way. Here is why. When LIGO detects a binary black hole merger and measures the masses of the two black holes, those masses encode the history of the system. A black hole with a mass of 30 solar masses got that mass somehow. It was either born with a progenitor star of a certain mass, or it accreted matter from a companion during a mass transfer phase, or some combination of both. The mass distribution of LIGO's black hole detections, the statistical pattern of how heavy the merging objects tend to be, is a fossil record of the population of binary star systems that produced them. To decode that fossil record, you need to understand the intermediate stages. You need to know how much mass a Wolf-Rayet star sheds before it collapses. You need to know how efficiently a compact object accretes from a stellar wind versus from direct mass transfer. You need to know how the orbital separation evolves during the mass transfer phase, and how supernova kicks modify the binary parameters, and how the spin of the compact object is affected by accretion. All of these questions have answers that can be constrained by studying systems like Cygnus X-3. Cygnus X-3 is, in this sense, a Rosetta Stone. Not because it is the only system of its type, but because it is the closest and best studied example we have of a compact object in the act of accreting from a Wolf-Rayet companion. The data we collect from Cygnus X-3, the mass transfer rate inferred from the accretion luminosity, the orbital evolution measured from the 4.8-hour period, the jet properties constrained by the radio observations, the compact object mass range estimated from the infrared spectroscopy. All of this feeds directly into the population models that gravitational wave astronomers use to interpret their detections. When a LIGO paper reports the merger rate of binary black holes per unit volume of the universe, that rate is calculated using models of binary star evolution that are calibrated against systems like Cygnus X-3. When those same papers report the inferred mass distribution of merging black holes, the theoretical predictions they compare against are built on our understanding of how Wolf-Rayet stars lose mass and collapse. The 2026 flare data, the multi-wavelength follow-up campaigns, the new constraints on the accretion rate and jet power, all of it is not just interesting in isolation. It is input data for a calculation that ultimately tells us something about the population of merging black holes that LIGO is detecting across billions of light years. There is a specific detail here that I want to make sure lands properly, because I think it is the most vivid way to understand the connection. On September 14th, 2015, LIGO detected the first gravitational wave event ever observed. Two black holes, one about 36 solar masses and one about 29 solar masses, merging approximately 1.3 billion light-years away. The signal lasted about 0.2 of a second in the detector band. The energy released in gravitational waves during that merger was equivalent to the mass energy of roughly 3 solar masses, more energy than the Sun will emit in its entire 10 billion year lifetime, released in a fraction of a second in the form of ripples in space-time. Those two black holes that merged in 2015, or rather 1.3 billion years ago, since that is how long the signal took to reach us, were once, billions of years before their merger, inside a binary system that looks something like Cygnus X-3. One compact object already formed, one massive companion star still alive, still losing mass, still feeding the accretion disk, jets possibly, flares possibly, an orbit completing in hours rather than days. A system that any astronomer observing that distant galaxy 1.3 billion years ago would have recognized immediately, because it would have looked just like what we see when we point our telescopes at Cygnus X-3 today. The radio flare detected at Russian 600 on April 6, 2026, is, in a sense, the sound of a gravitational wave source in formation. Not the final merger, that is billions of years away, and may never happen if the binary is disrupted by the supernova of the Wolf-Rayet companion. But the middle chapter of the story, the chapter that comes between the formation of the first compact object and the eventual merger of two. The chapter that is hardest to observe, hardest to model, and most consequential for understanding the population of merging compact objects that LIGO sees. The giant radio flares of 2026 are the early stages of a long evolutionary sequence that ends, if everything goes right for the system and nothing disrupts it, in a merger event billions of years from now. A merger that would send a continent of distorted space-time radiating outward through the universe at the speed of light. A signal that would register in whatever instruments exist to detect it as a chirp lasting fractions of a second, carrying encoded in its frequency sweep the entire history of the system that produced it. The radio flare detected in the Caucasus Mountains and the gravitational wave sweeping through Louisiana and Washington state are chapters from the same book. Written in different languages, one in radio waves, one in the geometry of space-time itself, separated by an unimaginable span of time, and yet telling the same underlying story about how gravity shapes matter at the most extreme densities the universe produces. We are reading the early chapters right now. The later chapters will not be written for billions of years, and the final chapter, the merger, the gravitational wave burst, the last signal from a system that was once the brightest radio source in the Milky Way, will travel outward from wherever Cygnus X-3 happens to be by then, in all directions, at the speed of light, looking for something to detect it. Whether anything will be listening, we cannot know, but the signal will be there, patient, as the universe always is, carrying its information across whatever distance separates the source from the receiver, the same way the April 6th flare carried its information across 29,000 light-years to reach a ring of metal panels in the Russian mountains on an otherwise ordinary morning in 2026. The universe tells its stories slowly. We are just lucky enough to be here for this particular page. Part 29, The Long Journey of the Signal. The signal that Russian 600 recorded on April 6, 2026, had been travelling for 29,000 years, and the journey it made through the galaxy is itself a story. The compact object launched the relativistic jet. The jet drove a shock into the Wolf-Rayet stellar wind. The shock accelerated electrons to relativistic energies. Those electrons spiraled in the compressed magnetic field at the shock interface and emitted synchrotron radiation in all directions. Some fraction of those photons, the radio wave photons in the 4.7 to 30 GHz range, were travelling in the general direction of where Earth would be 29,000 years later. They propagated through the immediate environment of the Cygnus X-3 system, through the dense Wolf-Rayet wind, through the bubble of shocked wind material surrounding the binary, into the general interstellar medium of the Milky Way. They crossed spiral arms, threaded through molecular clouds, travelled through regions of intense star formation and regions of quiet emptiness. They passed structures that did not exist when they were emitted and avoided catastrophes that occurred along their path after they had already left the scene behind. The galactic plane, dense with dust and gas, absorbed the optical frequencies completely. The radio photons, with wavelengths measured in centimetres, were long enough to slip through the dust grains unimpeded. They experienced dispersion, a slight frequency-dependent delay caused by the free electrons in the interstellar medium. They encountered magnetic fields that slightly rotated their polarization. But they survived, carrying the imprint of their origin, and arrived at a ring of metal panels in Russia at the speed of light, at 300 million meters per second, and were converted by the detector electronics into a data stream that was analyzed, classified, and reported to the global astrophysics community. The signal we received is not diminished by its journey. It is enriched by it. Every interaction it experienced in transit encoded information about the interstellar medium it passed through, and the event that generated it, the jet reactivation in January of 2026, was already the second in a series that is accelerating in frequency and not yet understood. The ancient signal arrived carrying a current mystery. The universe, patient as always, is waiting to see if we can read it. Part 30. The final mystery. So let us bring it all together and be honest about where we actually are. On April 6, 2026, a ring-shaped radio telescope in the Russian Caucasus mountains recorded a giant radio flare from Cygnus X-3, a binary system 29,000 light-years away in the direction of the constellation Cygnus. The flare peaked at 6.6 Jansky at 11.2 GHz, briefly making Cygnus X-3 the brightest radio source in the Milky Way. It was the second such event in approximately 80 days, following a January 2026 flare, with a smaller intermediate event in February. The compression of this timeline from the historical cadence of roughly 200 days between comparable events, or longer, is not explained by any current model of accretion disk and jet physics. The compact object at the centre of Cygnus X-3 is either a black hole or a neutron star, and after 60 years of observations, including data from X-ray satellites, radio arrays, gamma-ray space telescopes, and high-energy particle detectors, we cannot distinguish between these two options because the system is so heavily obscured by interstellar dust that optical and most infrared measurements are not possible. The mass of the compact object is constrained only to a range that straddles the neutron star to black hole boundary. The companion Wolf-Rayet star is shedding mass at an extraordinary rate through a dense stellar wind, feeding the accretion disk and creating the environment in which the radio flares occur. Whether recent changes in the mass loss rate of this star are driving the faster flare cadence is a hypothesis that is physically plausible but not yet confirmed. The system is simultaneously a microquasar, a gamma-ray binary, a local analogue of ultraluminous X-ray sources, and a pevatron accelerating particles to energies exceeding any human-built accelerator. None of these classifications individually, and no combination of them yet, produces a unified model that explains all the observed phenomena. The system is overdetermined by the data in a good scientific sense, meaning there are more measured properties than can be accounted for by the available theoretical frameworks, and the residuals of that mismatch are the frontier where the physics remains unresolved. And now the system is changing. The behaviour in 2026 is not simply a repeat of earlier behaviour at higher frequency. It is a qualitatively different behavioural mode, one that the observational record did not anticipate. Whether this represents the beginning of a sustained new high-activity state, a temporary excursion from which the system will return to its previous slower cadence, or the early signature of a more fundamental physical change in the system driven by the Wolf-Rayet companion's evolution, we do not yet know. What we know is that we are receiving more frequent messages from a system that we cannot fully read, that the messages are encoded in ancient light, in photons that left their source when the most sophisticated human technology was stone tools, and that they are arriving now, in a world with radio telescopes and space observatories and global communication networks and physics frameworks sophisticated enough to be surprised by what they detect. We have been watching Cygnus X-3 for 60 years. We have built extraordinary instruments. We have written thousands of papers. And the object is still, fundamentally, a mystery that refuses to resolve into a clean explanation. There is something appropriate about that. The universe is not obligated to be comprehensible on human timescales. The processes that drive Cygnus X-3 operate at energies and on scales that our theories approximate but do not fully capture. The 2026 flare acceleration is a reminder that astrophysical systems are not static puzzles waiting to be solved. They are dynamic realities that continue to evolve, to change, to produce new behaviour, to challenge the models built on their past behaviour. We are not just observing Cygnus X-3. We are trying to understand something that refuses to stay the same long enough to be understood, and that refusal, that persistent, patient resistance to final explanation, is perhaps the most honest thing the universe has ever said to us. The signal is still arriving, we are still listening, and we still do not fully know what we are hearing.